in the vast darkness of space, where time moves differently than it does on Earth, two great spiral galaxies are slowly drifting toward each other. The Milky Way, our home galaxy, and Andromeda, its nearest large galactic neighbor, are engaged in an ancient gravitational waltz that began billions of years ago. Tonight, let us begin a gentle journey through this cosmic story, one that unfolds across timescales so immense that human lifetimes are but fleeting whispers in comparison. The Milky Way stretches across the night sky like a luminous river of stars. It contains between 200 and 400 billion stars, each one a sun in its own right, many with their own families of planets orbiting in the darkness. Our galaxy measures approximately 100,000 light-years across, a disk of stars, gas, and dust rotating slowly around a supermassive black hole at its center. This black hole, known as Sagittarius A*, has a mass equivalent to about 4 million suns, yet remains invisible to our eyes, detectable only through the influence it exerts on nearby stars. Andromeda, known to astronomers as Messier 31 or M31, lies approximately 2.5 million light-years away from us. Despite this enormous distance, it is the closest large galaxy to our own, and on dark, clear nights away from city lights, you can see it with your naked eye as a faint, elongated smudge in the constellation that bears its name. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars, each contributing to the soft glow that has captivated human observers for thousands of years. These two galaxies have been aware of each other, in a gravitational sense, for most of their existence. Gravity, that patient and persistent force, reaches across the void of intergalactic space, gently pulling Andromeda toward us at a speed of approximately 110 kilometers per second. While this might seem fast by earthly standards, in cosmic terms, it is a slow, graceful approach, like two dancers gradually drawing closer across an impossibly vast ballroom floor. Scientists discovered this approaching merger through careful observation. In the 1920s, astronomer Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to identify individual stars in Andromeda, proving it was a separate galaxy far beyond our own. Decades later, using sophisticated instruments, astronomers measured the galaxy's motion through space by analyzing the light it emits. The Doppler effect, the same phenomenon that changes the pitch of a passing siren, reveals how objects in space move relative to us. Andromeda's light shows a blue shift, meaning it is moving toward us rather than away. This discovery transformed our understanding of the universe's future. Galaxies are not static islands frozen in space. They move, interact, and sometimes merge. The collision between the Milky Way and Andromeda has been inevitable for billions of years, written into the fabric of space-time by the distribution of matter in our local group of galaxies. The merger will not be violent in the way we typically imagine collisions. Space is so vast and empty that even when two galaxies interpenetrate, the stars within them almost never actually collide. The distances between stars are so immense that they will simply pass by each other like ghosts, their trajectories altered by the complex gravitational field created by the merging galactic masses. Instead of destruction, there will be transformation, a reshaping of both galaxies into something new. As you rest tonight, imagine yourself floating in the darkness between galaxies, watching these two magnificent spirals slowly approaching across the cosmic ocean. Time accelerates around you, millions of years passing in moments, and you witness the patient work of gravity drawing these stellar cities together. There is no sound in space, only the silent movement of countless stars, each following the invisible threads of gravitational force that bind the universe together. Let this image carry you gently into sleep, knowing that the cosmos continues its slow, majestic dance through the endless night. To understand the coming merger, we must first explore the structure of these galactic giants. Both the Milky Way and Andromeda are spiral galaxies, magnificent cosmic pinwheels that rank among the most beautiful structures in the universe. Tonight, let's wander slowly through their architecture, examining the components that make these galaxies what they are. The Milky Way consists of several distinct regions, each with its own characteristics. At the very center lies the galactic bulge, a dense, elliptical concentration of older stars that glow with a yellowish-reddish light. These stars formed billions of years ago when the galaxy was young, and they orbit the galactic center in random orientations, creating a spherical swarm around Sagittarius A star. The bulge measures roughly 10,000 light-years in diameter, a small but luminous heart at the galaxy's core. Extending outward from this central bulge is the galactic disk, a flat plane of stars, gas, and dust that contains most of the galaxy's visible matter. Our Sun resides within this disk, approximately 26,000 light-years from the galactic center, nestled in a minor spiral arm called the Orion Spur. The disk rotates around the galactic center, taking our solar system roughly 230 million years to complete one orbit, a period sometimes called a galactic year. Within the disk, spiral arms wind outward from the center like cream stirred into coffee. These arms are not solid structures, but rather density waves, regions where stars, gas, and dust accumulate temporarily before moving on. The Milky Way has several major spiral arms, including the Perseus arm, the Sagittarius arm, and the Scutum Centaurus arm. These arms glow brightly in photographs because they contain numerous young, hot, blue stars and regions of active star formation, where clouds of gas and dust collapse under gravity to ignite new suns. Surrounding the entire visible galaxy is the galactic halo, a roughly spherical region containing old stars, globular clusters, and vast amounts of mysterious dark matter. Globular clusters are densely packed spheres of ancient stars, each cluster containing hundreds of thousands to millions of stars bound tightly together by gravity. The Milky Way has approximately 150 known globular clusters, and they orbit through the halo like satellites, their ages often exceeding 10 billion years, making them among the oldest objects in our galaxy. Andromeda shares this basic structure, but on a slightly larger scale. Its disk spans approximately 220,000 light-years, more than twice the diameter of the Milky Way's disk. Andromeda's spiral arms are more tightly wound than ours, creating a more symmetric and arguably more photogenic appearance. The galaxy also possesses a double nucleus, an unusual feature discovered through detailed observations. This double structure may be the remnant of a past galactic merger, where Andromeda consumed a smaller galaxy, and the cores of both galaxies now orbit each other at the center. Both galaxies are surrounded by smaller satellite galaxies, gravitationally bound companions that orbit their larger host. The Milky Way has dozens of known satellites, including the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere. These satellites contain millions to billions of stars and will likely be absorbed by the Milky Way over time. Andromeda has its own retinue of satellite galaxies, perhaps as many as 25, each following elliptical orbits around their massive host. The visible matter in both galaxies, all the stars and gas we can detect, accounts for only a fraction of their total mass. The majority of each galaxy's mass consists of dark matter, a mysterious substance that does not emit, absorb, or reflect light. We know dark matter exists because of its gravitational effects. Stars in the outer regions of galaxies orbit faster than they should based on the visible matter alone. This discrepancy suggests the presence of enormous halos of dark matter extending far beyond the visible edges of galaxies, providing the additional gravitational pull necessary to explain the observed motions. As you drift towards sleep, picture yourself floating above the Milky Way, seeing it not as the band of light across Earth's night sky, but as an external observer would a magnificent spiral scene face on. The central bulge glows warm and golden, while the spiral arms wrap around it, traced by brilliant blue star-forming regions and dark lanes of interstellar dust. Around this luminous disk, invisible but present, the dark matter halo extends into the darkness, a ghostly sphere of gravitational influence that helps bind everything together. Now turn your gaze across the cosmic void to Andromeda, larger and equally beautiful, its light having traveled for 2.5 million years to reach your imagined vantage point. These are the two great structures that will, in time, become one. The realization that our galaxy would one day merge with Andromeda came gradually, built upon centuries of astronomical observations and increasingly sophisticated technology. Tonight, let us trace the gentle path of discovery that revealed our cosmic future, a journey that begins with ancient observers and leads to modern space telescopes. For thousands of years, humans noticed the faint, fuzzy patch of light in the constellation Andromeda. Persian astronomer Abd al-Rahman al-Sufi described it in the year 964, calling it a small cloud, in his book of Fixed Stars. To observers without telescopes, it appeared as nothing more than a dim, elongated smudge, one of many mysterious nebulous objects scattered across the heavens. The invention of the telescope in the early 17th century allowed astronomers to examine Andromeda more closely, but its true nature remained unclear for centuries. Was it a luminous cloud within our own cosmic system, or something far more distant? The debate continued through the 18th and 19th centuries, with various astronomers proposing different theories about these spiral nebulae seen scattered across the sky. The breakthrough came in the 1920s through the work of Edwin Hubble, using the powerful 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble identified individual Cepheid variable stars in Andromeda, stars that pulse with regular periods related to their intrinsic brightness. By measuring these pulsation periods and comparing them to the star's apparent brightness as seen from Earth, Hubble calculated their distance. The results were revolutionary. Andromeda lay far beyond the boundaries of the Milky Way at a distance of approximately 900,000 light-years by his initial calculations. Though later refined to 2.5 million light-years, this measurement proved that Andromeda was a separate island universe, a galaxy in its own right. This discovery fundamentally transformed humanity's understanding of the cosmos. The universe was far larger than anyone had imagined, filled with countless galaxies, each containing billions of stars. Our Milky Way was just one galaxy among multitudes, and Andromeda was our nearest large neighbor in this vast cosmic ocean. Understanding that Andromeda was approaching the Milky Way required another set of observations and insights. In the early 20th century, astronomer Vesto Slipher measured the spectra of various spiral nebulae, including Andromeda. By examining how the wavelengths of light from these objects were shifted, he could determine their motion relative to Earth. Most distant galaxies showed redshifts, indicating they were moving away as the universe expanded. But Andromeda showed a blue shift, revealing that it was moving toward us at approximately 300 kilometers per second, though this figure has been refined over the decades. However, knowing that Andromeda approaches us was not enough to predict a collision. The galaxy might simply be passing by, sliding past the Milky Way rather than colliding with it. Determining the galaxy's sideways motion, its proper motion across the sky, required extremely precise measurements over many years. This proved challenging because Andromeda's proper motion is incredibly small, shifting position on the sky by less than the width of a single pixel in most telescopes over the course of several years. The answer came from the Hubble Space Telescope, launched in 1990 and operating above Earth's distorting atmosphere. Between 2002 and 2010, astronomers used Hubble to measure the positions of stars in Andromeda with extraordinary precision, repeating the observations over several years to detect the galaxy's subtle motion across the sky. The team, led by Roland van der Merel at the Space Telescope Science Institute, spent years analyzing the data, accounting for every source of error and uncertainty. Their findings, published in 2012, confirmed what many astronomers had suspected. Andromeda's sideways motion is very small, not nearly enough to cause it to miss us. The galaxy is heading almost directly toward the Milky Way. A collision, or more accurately a merger, is inevitable. The research team calculated that the galaxies would have their first close passage in approximately 4 billion years, with the merger process continuing over several billion years after that. This discovery captured the public imagination, though astronomers were careful to emphasize that there was no danger to Earth or the solar system. By the time the merger occurs, our sun will be approaching the end of its main sequence lifetime, and conditions on Earth will likely have become inhospitable due to the sun's increasing luminosity. Moreover, the vast spaces between stars mean that actual stellar collisions during the galactic merger will be extraordinarily rare. As you settle into rest, imagine the countless hours astronomers spent gathering the data that revealed our cosmic destiny. Picture the Hubble Space Telescope, silently orbiting Earth, its instruments focused on a distant galaxy, patiently recording images over years, detecting motions so small they would be invisible to any ground-based telescope. This patience, this dedication to understanding our place in the universe, reveals something beautiful about the human spirit. Our desire to know, to understand, to see beyond our immediate surroundings and grasp the grand patterns that govern the cosmos. Let this knowledge bring you peace as you drift towards sleep, knowing that the universe unfolds according to laws we can comprehend, even when those laws operate on scales almost beyond imagining. The merger of the Milky Way and Andromeda will not happen overnight, nor will it resemble the explosive collisions we often imagine. Instead, it will be a slow, graceful transformation unfolding over billions of years. Tonight, let us walk gently through the predicted timeline of this cosmic event, imagining each stage as it might appear to an immortal observer watching from safe distance. We exist now in what we might call the prelude, with Andromeda approximately 2.5 million light-years away and approaching at roughly 110 kilometers per second. This approach has been occurring for billions of years already, guided by the mutual gravitational attraction between the two galaxies and influenced by the distribution of dark matter in our local group. From Earth, Andromeda appears as that faint smudge in the night sky, barely visible to the unaided eye, its light having traveled for 2.5 million years before reaching us. In approximately 2.5 billion years, Andromeda will have closed about half the current distance. At this point, the galaxy will appear significantly larger in Earth's night sky, assuming Earth still exists and has observers. The gravitational influence between the galaxies will begin to strengthen noticeably, though the effects on individual star systems will still be minimal. Tidal forces, the difference in gravitational pull across an extended object, will start to distort the outer regions of both galaxies, pulling streams of stars and gas toward the approaching partner. Around 3.5 to 4 billion years from now, the first close passage will occur. This moment, sometimes called first contact, marks when the outer halos of the two galaxies begin to interpenetrate. Andromeda will dominate Earth's night sky if our planet still has a breathable atmosphere and liquid oceans, though both are questionable given that the sun's increasing luminosity will likely have rendered Earth inhospitable by this time. The galaxy will appear as a vast, glowing structure, perhaps taking up a significant portion of the visible sky, a sight both magnificent and alien compared to anything humans have ever witnessed. During this first passage, The visible disks of the galaxies will not yet collide. Instead, they will approach closely, perhaps coming within a few 100,000 light-years of each other before their relative motions carry them apart again. However, this passage will not be without consequences. The gravitational interaction will distort both galaxies significantly. Spiral arms may be pulled out and stretched, creating long tidal tails of stars streaming into intergalactic space. Computer simulations suggest that these tidal tails could extend for hundreds of thousands of light-years, creating spectacular structures visible across vast reaches of space. After the first passage, the galaxies will separate again, but not for long. Gravity ensures they remain bound to each other, and they will swing back for subsequent passages. These encounters will occur roughly every 1 to 2 billion years, with each passage bringing the galactic centers closer together and further disrupting both structures. The ordered spiral arms will become increasingly chaotic, with stars pulled into new orbits that may be highly elliptical or tilted at various angles to the original galactic planes. Approximately 5 billion years from now, possibly during the second or third close passage, the merger will enter its most dramatic phase. The two galactic centers, each containing a supermassive black hole, will begin to spiral toward each other. This process, called dynamical friction, occurs because the black holes are so massive that they create gravitational wakes as they move through the surrounding sea of stars, similar to how a ship creates a wake in water. These wakes gradually slow the black hole's motion relative to each other, causing them to lose orbital energy and spiral inward. As the black holes draw closer, they will eventually form a binary system, two supermassive black holes orbiting each other at the heart of the merging galaxy. This phase may last millions of years, with the black holes gradually spiraling inward until they are separated by only a few light years, then light months, then light days. Throughout this inward spiral, they will emit gravitational waves, ripples in the fabric of space-time itself, though these waves will be at frequencies too low for current detectors like LIGO to observe. Finally, when the black holes come within a few million kilometers of each other, they will merge in a violent event that releases an enormous burst of gravitational wave energy. For a brief moment, this merger will be the brightest gravitational wave source in the universe, sending ripples through space-time that will propagate outward at the speed of light. The resulting black hole will have a mass approximately equal to the sum of the two original black holes, somewhere between 40 and 100 million solar masses. The final result, approximately 7 billion years from now, will be a single large elliptical galaxy. Computer simulations suggest this merged galaxy will no longer have spiral arms, but will instead be a roughly spherical or elliptical collection of stars. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkomeda, a blend of its parent galaxy's names. This new galaxy will contain all the stars from both the Milky Way and Andromeda, perhaps 1 trillion stars or more, spread across an elliptical volume several 100,000 light-years across. Within Milkomeda, individual stars will settle into new orbits, shaped by the combined gravitational field of the merged galaxy. Many stars will find themselves in different environments than they started in. A star that began near the edge of the Milky Way might end up near the center of Milkomeda, while a star from Andromeda's core might be flung outward into the merged galaxy's outer reaches. Some stars may be ejected entirely, thrown out of the galaxy by gravitational interactions and sent wandering through intergalactic space as lonely orphans. As you prepare for sleep, imagine witnessing this transformation in time-lapse, watching billions of years compressed into moments. Two great spirals approach each other across the darkness, their motions stately and patient. They touch, pull apart, touch again, each encounter more intimate than the last. Slowly, their separate identities blur and merge, spiral arms dissolving into a new, simpler form. Stars that knew the quiet suburbs of one galaxy find themselves in new neighborhoods, under new cosmic architectures. And through it all, most stars never come close to colliding, separated by vast gulfs of space even as their galaxies merge. It is transformation without violence, change on the grandest scale, and it continues the process that has been shaping galaxies since the early universe. Let this cosmic perspective ease you into rest. During this immense cosmic transformation, what might happen to planets, solar systems, and the possibility of life? Tonight, let's explore gently this question, examining what science tells us about planetary systems during galactic mergers and considering the fates of worlds like our own. Our solar system, as it exists today, is a relatively calm, stable environment. The Sun follows a nearly circular orbit around the galactic center, taking approximately 230 million years to complete each circuit. The 8 planets orbit the Sun in roughly the same plane, their paths predictable and stable over timescales of millions to billions of years. This stability has allowed life to develop and flourish on Earth over approximately 3.5 billion years. When the Milky Way and Andromeda merge, the Sun's orbit around the galactic center will change. Gravitational interactions during the close passages will alter the orbits of billions of stars, including our own. Computer simulations suggest several possible outcomes for our solar system. In some simulations, the Sun remains within the main body of the merged galaxy, settling into a new orbit within Milkomeda. In others, gravitational interactions during the merger process fling the Sun and its planets into the outer reaches of the new galaxy, or even eject them entirely into intergalactic space. However, it is crucial to understand that none of these scenarios pose a direct threat to the solar system's internal structure. The planets will continue orbiting the Sun just as they do now. The distances between stars are so vast that even during a galactic merger, close encounters between individual stars are extraordinarily rare. The nearest star to our Sun, Proxima Centauri, lies approximately 4.2 light-years away. Space is so empty that even when 2 entire galaxies interpenetrate, the stars within them almost never collide. To grasp this, imagine shrinking the Sun to the size of a grain of sand. On this scale, Earth would orbit about 3 centimeters away, and Neptune, the outermost planet, would be about 1 meter distant. Proxima Centauri, our nearest stellar neighbor, would be another grain of sand approximately 4 kilometers away. Now imagine 2 entire beaches of sand grains, each representing a galaxy, slowly passing through each other. The chance of any 2 specific grains colliding is infinitesimally small. This is the scale of emptiness in our galaxy, and the reason why stellar collisions during galactic mergers are so rare. Statistical analyses suggest that the probability of our Sun experiencing a close encounter with another star during the merger, close enough to significantly disrupt planetary orbits, is less than 1 in 100,000. Most likely, the Sun and its planets will simply find themselves in a different part of the merged galaxy, following a new orbit, but otherwise undisturbed. That said, Earth faces a much more immediate and certain threat than the galactic merger. The evolution of our own Sunday stars like the Sun generate energy by fusing hydrogen into helium in their cores. As they age, they gradually become more luminous, burning their fuel slightly more efficiently. Over the next billion years, the Sun's luminosity will increase by approximately 10%. This may not sound like much, but it will be enough to trigger a runaway greenhouse effect on Earth. As the Sun brightens, Earth's oceans will evaporate more quickly. Water vapor is a greenhouse gas, and more water vapor in the atmosphere will trap more heat, causing even faster evaporation. Eventually, within perhaps 1 billion to 1.5 billion years, Earth's oceans will have entirely evaporated. Without liquid water, life, as we know it, cannot survive. By the time the Milky Way and Andromeda have their first close passage in 4 billion years, Earth will likely have been a dead, desiccated world for billions of years. But what of other planets, other solar systems in both galaxies? The Milky Way contains billions of planets. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, astronomers have discovered thousands of planets around other stars, with more being found constantly. Current estimates suggest that most stars host at least one planet, and many host multiple planets. Extrapolating across the entire galaxy, there may be hundreds of billions of planets in the Milky Way alone. Many of these planets orbit within their stars' habitable zones, the range of distances where temperatures allow liquid water to exist on a planet's surface. The Kepler Space Telescope, which operated from 2009 to 2018, found that approximately 20 to 50% of Sun-like stars may have Earth-sized planets in their habitable zones. If even a small fraction of these planets develop life, the Milky Way could be home to millions or even billions of living worlds. During the galactic merger, each of these planetary systems will experience the same basic outcome as our solar system. Their internal structure will remain intact, but their location within the galaxy and their orbit around the galactic center will change. Most will never notice the merger in any direct sense. The night sky will change gradually over millions of years as the star's position within the galaxy shifts. But the planets themselves will continue their familiar orbits around their suns. For any civilizations that might exist on these planets, the galactic merger would present a spectacular sight in their night skies, assuming they survive long enough to witness it. The approaching galaxy would grow larger and brighter over millions of years, eventually dominating the sky. New stars would appear as the two galaxies interpenetrated, gradually changing the patterns of constellations that any civilization would have known for its entire history. But there would be no immediate danger, no sudden catastrophe, just a slow transformation of the celestial landscape. Some planetary systems might benefit from the merger. The gravitational stirring could compress gas clouds, triggering new waves of star formation. Young, newly formed stars would ignite, and some would quickly develop their own planets. These new solar systems, born from a merger itself, would be children of both galaxies, their parent stars forged from material contributed by both the Milky Way and Andromeda. As you drift towards sleep tonight, imagine a planet circling a distant star somewhere in Andromeda, a world perhaps covered in vast oceans beneath an alien sky. That planet is approaching us, along with its entire galaxy, moving through space at 110 kilometers per second. In some distant future, if that planet still exists, observers there might look up at night and see Milkomeda's stars stretching above them, a sky utterly transformed from the one their distant ancestors knew, yet their world continuing peacefully in orbit around its sun, unchanged despite the cosmic transformation occurring around it. Rest easy knowing that the universe, even in its grandest changes, maintains a gentle stability at the scale of individual worlds and the life they might harbor. One of the most beautiful consequences of galactic mergers is the triggering of intense star formation. Tonight, let us explore gently how the collision of the Milky Way and Andromeda will create new stellar nurseries, giving birth to millions of young stars, even as the galaxies themselves transform. Stars are born in clouds of gas and dust called molecular clouds, vast nebulae that can span hundreds of light years and contain enough material to form thousands or even millions of stars. These clouds consist primarily of hydrogen, the most abundant element in the universe, along with helium and trace amounts of heavier elements. For most of their existence, molecular clouds remain stable, their internal pressure balanced against gravitational collapse. However, certain events can disrupt this balance and trigger star formation. A shockwave from a nearby supernova, the gravitational influence of a passing star, or the compression of gas in a spiral arm can all cause regions within a molecular cloud to become dense enough that gravity overwhelms the outward pressure. Once this happens, the region begins to collapse, fragmenting into smaller clumps that will each potentially become individual stars. Galactic mergers are particularly effective at triggering star formation because they compress gas clouds through several mechanisms. As two galaxies approach each other, tidal forces stretch and squeeze the gas in both galaxies. When the galaxies interpenetrate, gas clouds from one galaxy can collide with gas clouds from the other. Unlike stars, which are so small and widely separated that they rarely collide, gas clouds are enormous and diffuse enough that they do collide and interact when galaxies merge. These collisions compress the gas, increasing its density and triggering gravitational collapse. Computer simulations of galactic mergers show that star formation rates can increase by factors of 10 to 100 during the most intense phases of a merger. Galaxies that might normally form a few solar masses worth of new stars each year can suddenly form tens or hundreds of solar masses of stars annually during a merger event. Astronomers have observed this process in many merging galaxies throughout the universe. One of the most famous examples is the Andromeda Galaxies, two spiral galaxies about 45 million light-years away that are currently in the process of merging. Images from the Hubble Space Telescope reveal bright, blue regions scattered throughout the merging system, each representing an active star-forming region containing thousands of young, hot stars. These regions glow brilliantly in ultraviolet light, a sign of vigorous star formation triggered by the collision. Another example is ARP 220, a merger system about 250 million light-years away. This system is producing stars at a rate approximately 100 times faster than the Milky Way's current rate. Observations with infrared telescopes revealed dense clouds of dust and gas in the galaxy's center, warmed by intense star formation hidden within. These starbursts, as astronomers call them, can create millions of new stars over just tens of millions of years. When the Milky Way and Andromeda merge, we can expect similar bursts of star formation. During each close passage, gas clouds in both galaxies will be compressed and stirred. The most intense star formation will likely occur when the two galaxies have fully merged and gas from both systems collides and accumulates near the center of the newly formed Milkomeda. This central region may experience a powerful starburst, creating millions of massive young stars in a relatively compact region. These newly formed stars will be hot and blue, burning their fuel quickly and brightly. The most massive stars, those with masses tens of times greater than the Sun, will live fast and die young, exhausting their fuel in just a few million years before exploding as supernovae. These explosions will enrich the surrounding gas with heavy elements, material that will eventually be incorporated into future generations of stars and planets. The star formation triggered by the merger will also create new planetary systems. Around many of the newly formed stars, disks of gas and dust will gradually coalesce into planets. These planets will be born into a galaxy very different from the one we know today, a galaxy that has been thoroughly mixed and transformed by the merger process. The heavy elements created by earlier generations of stars will be available to form rocky planets, and some of these worlds may eventually develop conditions suitable for life. Observations of star-forming regions in our own galaxy give us a preview of what these merger-triggered stellar nurseries might look like. The Orion Nebula, located about 1,300 light-years from Earth, is the nearest major star-forming region to us. It contains hundreds of young stars, many still surrounded by disks of material that may be forming planets. The nebula glows with a soft, greenish-pink light, illuminated by the ultraviolet radiation from hot young stars at its center. Delicate filaments of gas and dust thread through the region, sculpted by stellar winds and radiation. Another magnificent star-forming region is the Carina Nebula, approximately 7,500 light-years distant. This immense cloud spans more than 300 light-years and contains some of the most massive stars known, including Eta Carinae, a star system with a combined mass more than 100 times that of the Sun pillars of gas and dust, similar to the famous Pillars of Creation in the Eagle Nebula, rise within the Carina Nebula, each pillar potentially harboring embryonic stars within its dense core. During the Milky Way Andromeda merger, regions like these will multiply across the merging system. Vast nebulae will light up throughout Milkomeda, their colors ranging from the soft pinks of hydrogen emission to the deeper reds of cooler dust clouds and the brilliant blues of reflected starlight. For any observers lucky enough to witness it, the night sky during the peak of the merger's starburst phase would be spectacular, filled with glowing nebulae and clusters of brilliant young stars. As you settle into sleep, imagine floating through one of these future stellar nurseries. Around you, wispy clouds of gas and dust glow faintly with internal light, illuminated by forming stars hidden within. Here and there, brighter regions mark where stars have already emerged from their cocoons, their radiation pushing back the surrounding material and creating bubbles of cleared space. The scene is peaceful despite the violence of star birth, a slow-motion explosion of creation unfolding over millions of years. New suns ignite, new worlds begin to form, and the cycle of stellar generations continues, transforming cosmic chaos into the ordered beauty of solar systems. Let this vision of cosmic renewal carry you gently into rest. Not everything in the merging galaxies will be illuminated by starlight. Tonight, let us turn our attention to the dark matter that comprises most of each galaxy's mass, exploring gently this mysterious substance and its crucial role in the merger process. Dark matter is one of the most profound mysteries in modern astronomy. It does not emit, absorb, or reflect light, making it invisible to all our telescopes. Yet its gravitational influence is unmistakable. The existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who studied the Coma galaxy cluster and noticed that galaxies within the cluster were moving much faster than expected based on the visible matter present. Something invisible was providing additional gravitational pull. Further evidence accumulated in the 1970s when astronomer Vera Rubin measured the rotation curves of spiral galaxies. She observed that stars in the outer regions of galaxies orbit at nearly the same speed as stars closer to the center, which contradicted predictions based on visible matter alone. According to Newton's laws of gravity, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system orbit the sun more slowly than inner planets. The flat rotation curve suggested that galaxies are embedded in massive halos of invisible matter extending far beyond the visible disk. Current observations indicate that dark matter comprises approximately 85% of all matter in the universe, with normal matter, the atoms that make up stars, planets, and everything we can see, accounting for only 15%. Both the Milky Way and Andromeda possess extensive dark matter halos, each perhaps extending 3 to 4 times farther into space than the visible galaxy within. These dark matter halos will be the first parts of the galaxies to interact during the merger. Long before the visible disks of the Milky Way and Andromeda interpenetrate, their dark matter halos will begin to overlap and influence each other gravitationally. This interaction will help determine the timing and nature of the merger, as the distribution of dark matter affects how the galaxy's overall gravitational fields evolve. The nature of dark matter remains unknown. Scientists have proposed various candidates, with the most popular being weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass, but would interact with normal matter only through gravity and possibly the weak nuclear force, making them extraordinarily difficult to detect. Despite numerous experiments built deep underground to shield them from interference, scientists have not yet directly detected WIMPs or any other dark matter particle. Another candidate is the axion, a much lighter hypothetical particle proposed originally to solve a problem in particle physics, but later recognized as a potential dark matter component. Axions, if they exist, will be produced in enormous numbers, and their combined mass could account for the dark matter we observe. Experiments using extremely sensitive detectors are currently searching for axions, but as of now, their existence remains unconfirmed. A more exotic possibility is that dark matter consists of primordial black holes formed in the very early universe rather than from collapsing stars. These black holes would be much smaller than stellar mass black holes, perhaps with masses ranging from a fraction of Earth's mass to several times the Sun's mass. They would be effectively invisible, but would exert gravitational influence just like any other mass. However, various observations have placed constraints on this idea, suggesting that if primordial black holes exist, they cannot account for all dark matter. Regardless of its ultimate identity, dark matter plays a crucial role in structure formation throughout the universe. In the early universe, dark matter's gravity helped draw normal matter together, creating the seeds of the first galaxies. Today, dark matter provides the gravitational scaffolding that holds galaxies together and shapes the large-scale structure of the cosmos. Without dark matter, galaxies as we know them could not exist. The visible matter would not have enough gravitational pull to bind itself into stable structures. During the merger of the Milky Way and Andromeda, the dark matter halos will merge along with the visible galaxies. Computer simulations that include dark matter show how these halos distort and blend during the collision process. The dark matter doesn't simply mix uniformly. Instead, it forms complex structures with streams and concentrations developing as the merger progresses. Some dark matter particles from the Milky Way's halo will be flung outward into intergalactic space, while others will settle into the merged system's new, combined halo. One fascinating aspect of dark matter during galactic mergers is that it behaves differently from normal matter. Normal matter, primarily in the form of gas, can lose energy through electromagnetic radiation. When gas clouds collide, they heat up and radiate that heat away as light, causing the gas to lose energy and settle into new configurations. Dark matter cannot radiate energy this way because it doesn't interact electromagnetically. Instead, dark matter particles pass through each other like ghosts, influenced only by gravity. This difference affects the merger process. The visible matter, capable of dissipating energy, will eventually settle into a new equilibrium in the merged galaxy. The dark matter, unable to dissipate energy, will maintain a more extended, diffuse distribution. The final merged galaxy will thus have a relatively compact core of stars and gas, surrounded by a much larger, more extended halo of dark matter. Astronomers have observed this effect in other merger systems. The famous Bullet Cluster, approximately 3.5 billion light-years away, consists of two galaxy clusters that have collided and passed through each other. Observations using gravitational lensing, the bending of light by gravity, reveal that the dark matter halos pass through each other relatively undisturbed, while the normal matter, primarily hot gas, was left behind in the collision zone, having lost energy through electromagnetic interactions. This observation provides some of the strongest evidence for dark matter's existence and its unique properties. As you rest tonight, imagine the invisible architecture surrounding our galaxy. Extending far beyond the visible stars, a spherical halo of dark matter particles forms a ghostly sphere, perhaps 1 million light-years across. Each particle follows its own orbit around the galactic center, moving through space at hundreds of kilometers per second, yet never colliding with anything, passing through stars, planets, and even you without any interaction beyond the faint gravitational influence. Right now, at this very moment, countless dark matter particles are flowing through your body, through Earth, completely unnoticed, detectable only through their collective gravitational effect on the galaxy's rotation. Let the mystery of this invisible majority of our universe inspire a sense of wonder as you drift towards sleep, knowing that the cosmos contains depths we have only begun to explore. At the center of both the Milky Way and Andromeda lies a supermassive black hole, and when the galaxies merge, these titans will eventually spiral together in one of the most energetic events imaginable. Tonight, let us explore gently these cosmic giants and their inevitable union. Sagittarius A*, or SGR A*, as astronomers abbreviate it, is the supermassive black hole at the Milky Way center. It resides approximately 26,000 light-years from Earth, in the direction of the constellation Sagittarius. Despite being millions of times more massive than the Sun, SGR A* occupies a region smaller than Mercury's orbit. Its mass has been determined through decades of careful observation of stars orbiting near it. Beginning in the early 1990s, astronomers at observatories including the W. Keck Observatory in Hawaii and the Very Large Telescope in Chile began tracking individual stars near the galactic center. One star, designated S2 or S0-2, follows an elliptical orbit that brings it extremely close to SGR every 16 years. By measuring S2's position over multiple orbits, astronomers determined that it orbits an invisible object with a mass approximately 4 million times that of the Sun. The object's invisibility and extreme mass density leave little doubt. It must be a black hole. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon, the boundary of no return. Supermassive black holes like SGR A* formed in the early universe, though exactly how remains a topic of active research. They may have grown from smaller black holes that merged and accumulated matter over billions of years, or they may have formed directly from the collapse of enormous clouds of gas in the young universe. Andromeda possesses its own supermassive black hole, located at the galaxy's center and measured to have a mass between 100 million and 200 million solar masses, significantly more massive than SGR A*. This black hole also reveals itself through the motions of nearby stars, though Andromeda's distance makes these measurements more challenging than those conducted in our own galaxy. Interestingly, observations suggest that Andromeda may actually have two supermassive black holes at its center, orbiting each other. This unusual configuration likely resulted from a past merger with another galaxy, where Andromeda's original black hole captured the black hole from the smaller galaxy. If this interpretation is correct, it provides a preview of what will eventually happen when the Milky Way and Andromeda merge. Their central black holes will form a binary pair. When two galaxies merge, their supermassive black holes initially remain far apart, each still near the center of its respective galaxy's stellar distribution. However, as the galaxies settle into their final merged configuration, dynamical friction gradually causes the black holes to spiral toward each other. Stars passing near a black hole gravitationally interact with it, slightly altering both the star's trajectory and the black hole's momentum. Over millions of these interactions, the black holes lose orbital energy and spiral inward. The process accelerates as the black holes draw closer. When separated by a few light years, they begin to form a true binary system, orbiting their common center of mass. At this stage, gravitational wave emission becomes significant. According to Einstein's general theory of relativity, accelerating masses produce ripples in space-time called gravitational waves. Two massive black holes orbiting each other generate gravitational waves that carry away energy, causing the orbit to gradually shrink. As the black holes spiral closer, the gravitational wave emission intensifies. The frequency of the waves increases, rising from oscillations taking years to oscillations taking months, then days, then hours. Current gravitational wave detectors like LIGO and Virgo are sensitive to the final moments of black hole mergers involving stellar mass black holes, those with masses from a few to a few hundred times the Sun's mass. Supermassive black hole mergers emit gravitational waves at much lower frequencies, requiring different detection methods. Future space-based gravitational wave observatories, like the proposed Laser Interferometer Space Antenna, or LISA, will be designed to detect gravitational waves from supermassive black hole mergers. LISA will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart, using laser beams to precisely measure the distances between the spacecraft. When a gravitational wave passes through the system, it will subtly stretch and squeeze space, changing these distances in a detectable way. The final merger of the 2 black holes at the center of Milkomeda will release an enormous amount of energy in gravitational waves. In the last few minutes before merger, the black holes will orbit each other dozens of times per second despite each being millions of times more massive than the Sun. The gravitational wave signal will rise to a crescendo, a chirp that sweeps upward in frequency and amplitude before cutting off suddenly as the black holes merge into a single, larger black hole. This final black hole will have a mass approximately equal to the sum of the 2 original black holes, minus the equivalent of a few solar masses of energy radiated away as gravitational waves. The merger will leave the final black hole ringing like a bell, with the event horizon oscillating between various shapes before settling into a stable, symmetric form. These oscillations will also produce gravitational waves, gradually damping out over a period of hours. The merger of supermassive black holes may also produce electromagnetic signals. Gas and dust orbiting the black holes and accretion disks will be disrupted during the merger, potentially creating bright flares of radiation. However, the details of these electromagnetic signatures remain uncertain, as they depend on how much gas is present near the black holes at the time of merger. For observers within Milkomeda, the black hole merger will be invisible in conventional terms, as black holes by definition don't emit light. However, if any civilization has developed gravitational wave detectors, they will witness one of the universe's most spectacular events. The gravitational waves will pass through the entire galaxy, briefly stretching and squeezing all of space, though the effect will be far too small to notice without sensitive instruments. As you prepare for sleep, imagine the immense patience of these cosmic giants. 2 black holes, each millions of times more massive than the Sun, approach each other over billions of years. They spiral inward through a galaxy full of stars, their motion so gradual that millions of years pass between each decrease in their separation. Yet they are inevitable, bound by gravity's patient insistence. Eventually, in a final violent moment, they will merge, sending ripples through the fabric of space-time itself, announcing the completion of the galactic merger to the universe at large. Rest peacefully knowing that even these most extreme objects in the universe follow laws we understand, their behavior predictable despite their otherworldly nature. The merger of the Milky Way and Andromeda will not occur in isolation. These galaxies exist within a larger structure called the local group. And tonight, let us explore gently how the entire neighborhood of galaxies will evolve as the 2 giants collide. The local group is the small cluster of galaxies that includes the Milky Way, Andromeda, and approximately 80 other known galaxies, most of them much smaller dwarf galaxies. This group spans approximately 10 million light-years across, a modest size compared to large galaxy clusters like the Virgo cluster or the Coma cluster, which contain hundreds or thousands of galaxies. Within the local group, the Milky Way and Andromeda are the 2 dominant members, each massive enough to gravitationally influence the entire group. The 3rd largest member is the Triangulum Galaxy, also known as Messier 33 or M33, a spiral galaxy containing perhaps 40 billion stars, significantly smaller than either the Milky Way or Andromeda. Triangulum lies about 3 million light-years from Earth, relatively close to Andromeda, and appears to be gravitationally bound to it. Computer simulations suggest that Triangulum will likely be involved in the merger as well, though its exact fate varies depending on initial conditions. In some simulations, Triangulum merges with Andromeda before Andromeda collides with the Milky Way, making the eventual collision a three-way merger. In other simulations, Triangulum orbits the Milky Way-Andromeda system for some time before eventually being absorbed into Milkomeda. Either way, this third galaxy will likely become part of the merged system within 10 billion years. The local group also contains numerous dwarf galaxies, small galaxies containing anywhere from a few million to several billion stars. The Milky Way has many dwarf galaxy satellites, including the large and small Magellanic Clouds, visible as faint cloudy patches in the southern hemisphere's night sky. These two irregular dwarf galaxies orbit the Milky Way at distances of approximately 160,000 and 200,000 light-years respectively. The Large Magellanic Cloud contains roughly 30 billion stars and is actively forming new ones. The Tarantula Nebula, also known as 30 Doradus, within the Large Magellanic Cloud, is one of the most active star-forming regions known, a vast complex where hundreds of massive young stars have recently ignited. The Small Magellanic Cloud is slightly smaller and more irregular, containing perhaps 3 billion stars. Both Magellanic Clouds are slowly being disrupted by the Milky Way's gravity. Tidal forces are pulling streams of gas away from them, creating the Magellanic Stream, a long arc of neutral hydrogen gas that extends across more than 100 degrees of the sky. Eventually, perhaps in a few billion years, both Magellanic Clouds will likely be torn apart and absorbed by the Milky Way, their stars scattered among our galaxy's halo. Other dwarf satellites of the Milky Way include the Sagittarius dwarf Elliptical Galaxy, currently in the process of being torn apart by tidal forces as it passes through the Milky Way's disk, and the Canis Major dwarf, another small galaxy in the process of being absorbed. These mergers are ongoing examples of the hierarchical process of galaxy formation, where larger galaxies grow by consuming smaller ones. Andromeda possesses its own system of satellite galaxies. Messier 32, or M32, is a compact elliptical dwarf galaxy orbiting close to Andromeda's center. Messier 110, or M110, is another elliptical dwarf satellite. Both are visible in telescopes near Andromeda's bright core. Like the Milky Way satellites, Andromeda's smaller companions will eventually be absorbed during or after the merger with the Milky Way. When the Milky Way and Andromeda merge, the fate of these satellite galaxies becomes complex. Some may be stripped away from their parent galaxies during the close passages, sent on new orbits through the local group. Others will remain bound and will eventually settle into orbits around Milkomeda. A few might be flung out of the group entirely, ejected into intergalactic space to wander alone through the cosmos. The local group itself exists within a larger structure called the Virgo supercluster, or more recently recognized as part of the even larger Laniakea supercluster. These superclusters are among the largest structures in the universe, containing tens of thousands of galaxies spread across hundreds of millions of light-years. The Milky Way, along with the entire local group, is slowly moving toward the Virgo cluster, the nearest large galaxy cluster, under the influence of its enormous gravitational pull. However, this motion toward Virgo is relatively slow, and the merger with Andromeda will occur long before the local group reaches Virgo. After the merger creates Milkomeda, this new, larger galaxy will continue moving through the supercluster, gradually approaching other structures. Eventually, billions of years after the Milky Way-Andromeda merger, Milkomeda may itself merge with other galaxies, perhaps eventually becoming part of a massive elliptical galaxy at the center of a large cluster. The expansion of a universe complicates these long-term predictions. Galaxies beyond the local group are generally receding from us as space itself expands, a phenomenon discovered by Edwin Hubble in the late 1920s. Dark energy, a mysterious force causing the expansion to accelerate, drives distant galaxies away from us at ever-increasing speeds. Only galaxies within gravitationally bound structures like the local group or galaxy clusters can resist this expansion and eventually merge. This means that while the local group's galaxies will likely all merge together over the next tens of billions of years, more distant galaxies will forever remain out of reach. The Virgo cluster, despite its gravitational attraction, may recede faster than we can approach it if dark energy's influence continues to accelerate the universe's expansion. In such a future, Milkomeda and any other merged remnants of the local group will become increasingly isolated, surrounded by an expanding void as other structures recede beyond the cosmic horizon. As you settle towards sleep, picture the local group as a small island of matter in the cosmic ocean. A few dozen galaxies, bound together by gravity, orbiting a common center, engaged in a slow dance that will eventually bring them all together. The two largest members, the Milky Way and Andromeda, lead this dance, their eventual merger initiating a cascade of interactions that will reshape the entire group. Smaller galaxies orbit like moons around planets, their fates tied to their massive neighbors. And beyond this small island, other islands, the ocean, most of them drifting farther away as the universe expands, leaving each island to evolve in increasing isolation. Let this vision of cosmic structure, of order emerging from gravity's patient work, ease you into peaceful rest. As we conclude our journey through this cosmic merger, let us look gently toward the deepest future, imagining what might lie ahead for Milkomeda and the universe beyond. Tonight, we contemplate timescales that dwarf even the billions of years required for the galactic merger itself. 7 billion years from now, the merger will be complete. Milkomeda will shine as a large elliptical galaxy, its trillion stars settling into their new orbits within the merged system. Star formation, intense during the merger, will have slowed as the available gas is consumed or heated to temperatures too high for new stars to form. The galaxy will gradually redden as massive, short-lived blue stars exhaust their fuel and die, leaving longer-lived red and yellow stars to dominate the stellar population. Our sun, if it still exists at this point, will be in its final stages. Stars like the Sun live approximately 10 billion years on the main sequence, the stable phase during which they fuse hydrogen into helium in their cores. In about 5 billion years, roughly the same time as the first close passage with Andromeda, the Sun will exhaust the hydrogen in its core and begin evolving into a red giant, expanding enormously as it starts fusing hydrogen in a shell around an inert helium core. As a red giant, the Sun will swell to perhaps 100 times its current diameter, its outer layers extending past Mercury's orbit, possibly reaching Venus or even Earth. The inner planets will likely be engulfed and destroyed. Earth, if it survives, will be scorched beyond recognition, a blackened cinder orbiting what remains of our star. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will survive this phase, though their atmospheres may be significantly altered by the increased radiation. Eventually, the Sun will shed its outer layers in a planetary nebula, a beautiful shell of glowing gas expanding into space, illuminated by the hot stellar core left behind. This core, no longer generating energy through fusion, will cool slowly over billions of years, becoming a white dwarf, an Earth-sized ember gradually fading from white to yellow to red and eventually to black. Throughout Milkomeda, similar stellar evolution will continue. Stars will be born from remaining gas clouds, live their lives, and die according to their masses. The most massive stars will explode as supernovae, briefly outshining billions of ordinary stars, scattering heavy elements into space, and sometimes leaving behind neutron stars or black holes. Less massive stars will follow paths similar to the Sun, ending as white dwarfs. The smallest stars, red dwarfs with masses less than half the Sun's, will burn their fuel so slowly that they can continue shining for trillions of years, far longer than the current age of the universe. After approximately 100 billion years, star formation in Milkomeda will effectively cease. All available gas will have either been incorporated into stars, heated to temperatures preventing collapse, or ejected from the galaxy by stellar winds and supernovae. The galaxy will contain only long-lived stars, white dwarfs, neutron stars, and black holes. This marks the beginning of what cosmologists call the degenerate era, when normal stars no longer exist, and the universe is populated primarily by stellar remnants. Red dwarfs will continue burning for trillions of years, gradually exhausting their fuel and cooling into white dwarfs. By the time the universe is perhaps 100 trillion years old, even the longest-lived red dwarfs will have exhausted their fuel. Milkomeda will consist entirely of degenerate objects, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and other cold debris. These stellar remnants will not remain in stable orbits forever. Through a slow process called dynamical relaxation, gravitational interactions between objects will gradually redistribute energy within the galaxy. Some objects will gain energy and be ejected into intergalactic space. Others will lose energy and fall toward the galaxy's center, eventually feeding the supermassive black hole that formed from the merger of SGR and Andromeda's black hole. Over timescales of perhaps 10 to the 20th power years, most of Milkomeda's stars and stellar remnants will either be ejected from the galaxy or fall into the central black hole. The galaxy will evaporate, leaving behind a much smaller, denser cluster of objects orbiting the central black hole, surrounded by a vast halo of ejected stellar remnants drifting through intergalactic space. Even white dwarfs and neutron stars may not be stable forever. Some theoretical models suggest that protons, the particles that make up atomic nuclei, may eventually decay with a half-life of perhaps 10 to the 34th power years. If proton decay occurs, white dwarfs and neutron stars would slowly dissolve into lighter particles and radiation, leaving black holes as the only remaining large-scale structures in the universe. Black holes themselves will not last forever. Stephen Hawking showed, theoretically in 1974, that black holes emit radiation through quantum effects near their event horizons, a process now called Hawking radiation. This radiation causes black holes to slowly lose mass and eventually evaporate completely. The time required for this process depends on the black hole's mass. Stellar mass black holes would take perhaps 10 to the 67th power years to evaporate, while supermassive black holes like the one at Milkomeda's center might take 10 to the 100 power years or longer. Eventually, after timescales almost beyond comprehension, even these black holes will evaporate, leaving behind only radiation slowly spreading through an ever-expanding universe. If the expansion continues accelerating due to dark energy, the universe will become increasingly cold, dark, and empty, with any remaining particles separated by distances too vast for them ever to interact. This possible endpoint is sometimes called the heat death of the universe, a state of maximum entropy where no further significant events can occur. However, these predictions rest on current understanding, which may be incomplete. Physics may hold surprises that alter these long-term forecasts. New forms of matter or energy, or new fundamental forces, could emerge at energies or timescales we haven't yet explored. The universe may be far stranger than our current theories suggest, Despite these deep future speculations, one thing seems certain. The universe is finite in neither space nor time. Events will continue to unfold according to physical law across timescales that make the age of the universe thus far seem brief. The merger of the Milky Way and Andromeda, momentous as it seems to us, is just one chapter in a story that may never truly end, though it may transform into forms we cannot yet imagine. As you drift into sleep tonight, let your mind rest with this vast perspective. The universe is ancient, but it is also young, with most of its history still lying ahead. Our existence, brief and fragile as it is, occurs during a remarkable epoch when stars shine, galaxies merge, and the cosmos remains vibrant and dynamic. We are privileged to witness this particular moment in cosmic history, to understand our place within it, and to contemplate the deep past and distant future with minds evolved to wonder. Rest peacefully knowing that the universe, vast and ancient though it is, operates according to laws we can comprehend, its grand patterns accessible to patient observation and careful thought. May your dreams be filled with stars, with galaxies dancing across the darkness, and with the quiet wonder of existence itself.